Hello, everyone, and welcome to Dana-Farber's Department of Data Science Frontiers in Biostatistics webinar. My name is Erica Fike, and I'm the program manager for the department. If you have a question for the speaker or the organizers, we ask that you please use the Q&A tab in the Zoom portal, and we will answer all the questions after the talk. Our faculty organizers will manage that session. With that, I will turn it over to Svetlana Tykocheva to introduce our speaker.
Thank you, Erica. And it's a great pleasure today to welcome Dr. Fan Li. Dr. Li is an assistant professor in the Department of Biostatistics at Yale School of Public Health. He joined Yale School of Public Health in 2019 after he earned his doctoral degree in biostatistics from Duke University. Dr. Li is a faculty member at the Yale Center for Methods in Implementation and Prevention Science and then the Yale Center for Analytical Sciences, as well as other centers that are devoted to research on various diseases such as AIDS and Alzheimer's disease. Dr. Li's research aims to develop and improve statistical methods for designing and analyzing pragmatic clinical trials, and in particular cluster-randomized and stepped wedge trials. He has also developed causal inference methods for estimand-aligned analysis of randomized trials and observational studies, as well as techniques for improving internal and external validity to facilitate unconfounded treatment comparisons under different study designs. Dr. Li co-authored over 90 peer-reviewed articles and developed multiple R packages and Stata modules, implementing his methods for everyone to use. His work is supported by Patient-Centered Outcomes Research Institute and NIH. He's a principal investigator of multiple funded projects that investigate novel study design and causal inference methods in pragmatic trials. And today, Dr. Li will tell us about model robust and efficient covariate adjustment for cluster randomized experiments. Thank you very much. So we can get started whenever you're ready with the talk.
Thank you so much for your nice introduction, and thanks for your invitation. It's a great pleasure of mine to be here and connect with us on this topic that I'm really enthusiastic about. So I'm going to talk about model robust and efficient covariate adjustment for cluster randomized experiments in the next hour. And so to start with, a quick background, cluster randomized experiments or cluster randomized trials are those designs where we randomize the entire clusters to receive intervention or control condition rather than randomizing individuals themselves. And so these trials are often used when the intervention is naturally implemented in the cluster level or to avoid treatment contamination had we randomized at the individual level. And a cluster could be a hospital, a clinic, a classroom in the educational setting, or a village in the infectious disease setting. And in these trials, by design, because the clusters will be randomized, all the individuals in the cluster will be exposed under the same intervention condition within the cluster. And a treatment that often gets evaluated in this context could include a training program, a healthcare delivery approach, or a policy change, among others. And the overarching goal is to evaluate whether the intervention works in that population we are interested in, and to study or report the overall intervention effect. The cluster randomized trials or experiments are increasingly popular in pragmatic trials, which is a very popular concept these days. NIH has a initiative back in 2012 that supports the national efforts to build infrastructures for conducting pragmatic trials. And among over 20 demonstration projects supported within that collaboratory, there are at least 16 studies that are cluster randomized trials, and only 1 or 2 that are individually randomized. And on this topic, there are more than one classic textbooks that formalizes the guidance and statistical methods for designing and analyzing cluster randomized experiments or trials. And they deliver a consistent message that is, we no longer rely on simple models that address IID data in this context. We want to have models where we take into account the inter-cluster correlation coefficient, or ICC, of the outcome, such as a random effects model or generalized estimating equations approach, with a non-identity working correlation to properly adjust for the non-independent natures of the outcome. And under those models, a lot of the methods has been developed and elucidated on designing and analyzing these trials. And so the primary interest in this design is to estimate the intervention effect. And a common practice is to take the model and believe that model is the model that generates the data, and then report the coefficient of the model as the intervention effect. And just to elaborate on that, our outcomes that are often collected in this context has a multi-level structure. We have individual level outcomes for each patient collected, but patients are nested typically in clusters that are higher level unit. To control for the intra-cluster correlation coefficient, the linear mixed model or generalized two mainstream and knowledge that we learned from traditional RCTs can be translated into this context so that we could also control for baseline covariates, which we believe would be prognostic of the outcome, and that could improve the study efficiency. But with all those moving parts, we still report the coefficient of the treatment variable in a regression model and take that as the average treatment effect. And despite the fact that it is a common practice to do so, a potential challenge in interpretation is that the treatment effect estimand is defined based on a model we postulate for the data at hand. And that estimand may change with the link function specification, the covariates specification or inclusion, as well as the random effects or working correlation model specification in an unexpected way, which we will elucidate in a minute. And if the model is not the data generating process, then it is really not clear what treatment contrast does this beta coefficient in a model represent. And so this is a schematic of the conventional wisdom where we have our data collected in a cluster randomized experiment, and we fit a model that we have access to in our toolbox, which may contain restrictive assumptions, such as whether we have one covariate or no covariates, or some assumptions on how the correlation can be modeled. And then we take the coefficient of the treatment variable and treat that as an overall summary of the intervention effect. And we interpret that as our average intervention effect. But if the model is wrong, the interpretation is generally less well studied, and it's not clear as to what that parameter targets. And this is just a quick and simple illustration on when things might go wrong. And so on the left-hand side, we have a very basic simulation scenario where we assume that the data are actually generated according to a generalized estimating equation model with only the treatment variable included in the mean model. So the mean model is correctly specified. And the only differences in these four dots in each of the panels is whether we have used an independence working correlation or an exchangeable working correlation. So the IEE stands for independence estimating equation, and the EEE stands for exchangeable estimating equation. And we use this W letter to indicate whether we further reweight the clusters by the inverse cluster size. Sometimes we believe that we don't want the large clusters to dominate. We might want to inverse weight by the cluster size. And so when the cluster size as a feature in these trials is not informative in a sense that the treatment contrast in a cluster is independent of the cluster size, then everything is all good. We have the traditional well-studied scenario where the only difference across these methods is how we could potentially improve efficiency by using an exchangeable correlation matrix or by using some kind of inverse cluster size weights. But if the cluster size is a proxy of some prognostic covariates or potential effect modifiers in the sense that maybe large clusters have a better practice and they learn much, much faster. So there is an effect modification based on some proxies that we don't observe, but that proxy is related to the cluster size. Then we get into trouble because the limit of the coefficient under different statistical decisions can diverge. And then as we introduce later on, there are two estimands we might be interested in, and only two choices of the GE specifications lead to consistent estimation. And if we do complex things, we get very different results than what we want to estimate. And that could be a problem. And so over time, because of this issue that arises in the multi-level data context, there is a progression toward estimand aligned analysis of cluster randomized experiments, but the majority has been developed under the randomized based inference paradigm, where the where the variability is driven by randomization instead of sampling. There has been much less development under the sampling-based inference paradigm, which interestingly is what we rely on for understanding model-based analysis. We often assume our unit of randomization or unit of inference goes to infinity, and then we derive the asymptotic theory for that. So coming into this question, we had two sub-questions. The first one is, given these developments and given the complexity of analysis of cluster randomized experiments and the confusion toward estimands, how can we achieve robust inference with these mainstream model-based methods so that they could generate valid inference to the target estimate we wanted, even when these models were incorrectly specified? And we could possibly leverage the randomization as a mechanism to generate valid inference. And in addition, maybe that is not sufficient. We also want to make sure we have the largest statistical power to identify the treatment signal. So then how do we maximize statistical efficiency by leveraging covariate adjustment, but not compromising the consistency to the target estimates? And so we want to address these two questions in this presentation. And so our contributions of this work is that for parallel arm cluster randomized trials, we want to introduce principled strategies for estimand aligned analysis that allow for covariate adjustment. And to do so, we first adapt generalized estimating equations and linear mixed model estimators in a way so that we could achieve model robust inference. And we identify the sufficient conditions under which this actually holds. And that gives us some flexibility in the model misspecification spaces. And in addition, maybe that's not sufficient, that's not well enough. We want to also study a class of estimators that are motivated by the so-called efficient influence functions, which are a class of estimand-oriented tools that summarize the data and then offer us honest inferential tools to target estimators and possibly in an efficient way. And so we show that if we estimate working models using parametric regression, we get robustness properties very similar to double robust property in these modern estimators in causal inference, as well as the fact that if we leverage machine learners to flexibly learn these working models, we get an efficient estimator that achieve the variance lower bound. And so in this development, we would also allow for the cluster size variation depend on the treatment assignment and possibly cluster level covariates. So we do address that to an extent that we could accommodate a form of selection bias. And just to proceed, we want to showcase one simple scenarios on why there could possibly be biases and on what is actually the deal with estimands in this context. So let's consider a very simple example, a hypothetical cluster randomized trial with only 6 clusters. And suppose we have half of the clusters are large clusters that contains 100 individuals. That's cluster 4 to 6. And in these clusters, let's assume that hypothetically, the intervention effect in these clusters are relatively small, which is 1. And we have another 3 clusters that are relatively small, so only 10 individuals. That's cluster 1 to 3. And we assume that the true causal effect in those clusters are relatively large, say 5, maybe because the physicians can give more attention to the individuals in those clusters. And then if we summarize the true causal effect as an average across all individuals in the trial, we get 1.4 as our target parameter of interest. But if we summarize the intervention effect as an average across the clusters in the trial, let's weigh the clusters equally, regardless of the cluster size, then we get 3, which almost doubled the value that we generate by summarizing the individual level contrast. And this sharp difference is mainly because the cluster size is an effect modifier of the intervention effect in these trials, or could be associated with other unmeasured effect modifier of the true causal effect in these trials. And so the difference can be substantial depending on how the variation of the treatment effect is dependent according to the cluster size variation. And in fact, both estimands can be relevant in this context. The individual average causal effect, or IATE, addresses the question that what is the expected change in outcome associated with treatment for a typical patient? And for instance, if we have an intervention delivered to patients aiming to reduce mortality, then this IATE estimate may be of interest, as it represents the population impact of switching from control to intervention. And that is an individual level, an individual population level concept. The cluster average causal estimand, or CATE, answers the question of what is the expected change in outcome associated with treatment for a typical provider or clinic and its natural patient panel. And for instance, in a trial aiming to reduce unnecessary prescribing of antibiotics to patients in which doctors act as clusters, then the CAT estimand may be of interest, as it provides the intervention's effect on the clinician's prescribing habits. So that is naturally a cluster level concept, or cluster level contrast. And we could formalize this concept using the potential outcomes framework to lay the ground for this work, in which we assume Yij1 to be the outcome for individual J in cluster I, if cluster I were assigned to treatment counterfactually, and we define Yij0 in a similar way. We write Ni to be the source population size for each cluster, and that could just be what we consider to be the total number of eligible individuals that we want to study if we plan a specific study. And we assume a total of n clusters that we have utilized in the specific trial. To define these potential outcomes, we assume the cluster level stable unit treatment value assumption, in which case we rule out between cluster interference. And so the individual level outcome will only depend on the cluster level assignment for the clusters to which that individual belongs. Individual level stable unit treatment value assumption in this context, however, is less relevant because cluster randomization already ensures that everybody in the cluster has the same intervention. So we could, under these conditions, define Yij1 and Yij0 unambiguously. And then we write the cluster average potential outcome in a way that we summarize the potential outcome in a cluster first, and we take the mean, and then we take the expectation across the cluster population. So that is defined as the cluster average potential outcomes. And based on that, we could create cluster average causal estimand on the difference scale as a risk difference, or on the ratio scale. For example, by contrasting mu C1 to mu C0, then we get a causal risk ratio defined on the cluster average sense, and so on. And in parallel, we could define the individual average potential outcomes in a way such that it is a ratio of two expectations, the ratio level expectation of the sum of the potential outcomes in a cluster versus the ratio of the cluster size. And so this concept might be a little easier to understand if we take the expectation out and we use an empirical expectation for the sign of E here, then we immediately see that the mu IA is a overall average when we collapse all the individuals from different clusters into a single population. And that actually does not differ conceptually from what we target in an individually randomized control trial. And so once we have these individual level average potential outcomes defined, we could create causal estimand or IATE on the difference scale or on the ratio scale in a very similar fashion. And so in this work, we observe data at two levels, and we want to write them down. At the cluster level, we let AI denote the cluster level assignment of treatment. And so 1 for treatment and 0 for control. And we write CI as the cluster level covariates. And so this could be characteristics of the cluster, such as whether the location is in an urban area or in a rural area. And we assume we have access to the source population size Ni on a which is defined over a finite support on integers. And we'll discuss this condition as we move forward. We might not observe everybody in the source population in a real study, and we assume that we observe Mi out of the Ni individuals for a specific cluster. So that's a subset. This framework does assume that a good estimate of Ni is available in our study. And in which case, in cases where this is not plausible, we could simply set Ni equal to Mi, and our estimators will still proceed without problems. At the individual level, we write Xij as the individual level covariates, which can be age, demographics, or clinical information of the individuals we recruit. Because we do observe only a subset of the entire source population, within a cluster, we can define a sampling indicator Sij to indicate whether an individual we observe is sampled versus not. And so for everybody in our study that we have data, obviously Sij equals to 1. And then we write our observed outcome to be Yij. We also want to emphasize that we only get to observe one potential outcome, as that's the fundamental question of causal inference. And we allow Sij and Yij to link with their potential values. And so we have Yij equal to Ai times Yij1 plus 1 minus Ai times Yij0, depending on the revealed assignment of treatment at the cluster level. We observe Yij1 or Yij0, and the same idea carries forward to the sampling indicator, because in these trials, in the majority of the cases, the clusters were randomized first before individuals were recruited or enrolled. And so inherently, the cluster size may be a post-randomization concept. And so we let Sij1 and Sij0 to define the potential sampling indicator at the individual level under the treatment or control condition. And we only observe Sij depending on the assignment of treatment at the cluster level. So to proceed, part of this work is to build a framework under which we could make inference in a rigorous way. We could infer the causal estimands we have defined under either model-based inference or possibly improved version of those estimators. And so to proceed, we write Yia to be the collection of the potential outcomes under condition A for each cluster, and we collect Sia in a similar way. We define Xi as the collection of the covariate vector across individuals in the source population for each cluster. And so notice that when we define Yi, Si, and Xi, these are going to be the collections of information across individuals in the source population. So to proceed, assumption one assumes that if we define the collection of the random variables in a cluster as Wi, that's literally everything that we can possibly define for a cluster, we assume that these random vectors are mutually independent across clusters. And this is actually plausible in many settings because the clusters may be geographically distant, and so they don't interact with each other. It's also a common assumption made in the correlated data world where we do have between cluster independence. We assume that the source population size Ni follow an unknown distribution over a finite support on the positive integers. And given the cluster size in the source population, then Wi follows an unknown distribution with finite first and second moments. And so condition A, we have said already, assumes between cluster independence, but it allows these variables to be correlated within a cluster in an arbitrary way. And then assumption B and C is considered to ensure that marginally these W vector can follow a common distribution, even though they may have varying dimensions because of the fact that Ni can be different. In addition, we assume cluster randomization. And this condition is oftentimes easier to comprehend because that's by design. That's what we have by design. We assume that the cluster level treatment indicator is an independent realization under a Bernoulli design. So a flip of a coin, and it holds automatically because we have this design. And even though we do not discuss stratified randomization, but we could extend the work to accommodate that with some additional complexities that we will not address in this talk. And once we have assumed the population framework and the random assignment of the cluster level treatment indicator, we need to address the fact that we don't observe everybody in a cluster. So we might have a second stage sampling, which we assume here. We assume that the cluster size is a post-randomization concept in a sense that the cluster size M can depend on the treatment assignment. But we first assume that the cluster size is independent of any other variables that we observe or unobserved. So it is an independent realization once we condition on the treatment assignment. And once we have the cluster size, we would assume that the within cluster sampling is completely random according to that cluster size. And for instance, the cluster size Mi may be 10 plus a random integer. So it's a completely random cluster size we might observe for each cluster. Or in addition, we assume Mi is a function of the treatment indicator. So we might be in a situation where we could possibly recruit more individuals in the intervention cluster versus in a control cluster. And that could happen because these trials were never blinded. And so individuals know where they might want to seek treatment if a cluster is randomized to the intervention condition. And this assumption may be restrictive, but is a good starting point for us to discuss the model robustness features of these estimators. And admittedly, even though they were never written out very explicitly, this condition were oftentimes assumed when we fit models to cluster randomized trials. It's only that we never spell it's only that we never spell them out very clearly. And so we want to investigate under these setups that are relatively more rigorous as to what we are studying, the conditions. We want to investigate when are model-based methods robust. And we focus on GE and linear mixed models because they were used in the majority of the published reports that adopt cluster randomized designs. And these models can be complicated because the random effect specification or working correlation specification can induce weighting in a way that we don't realize and mess up with the estimands that we want to target. Just to summarize that shortly, that is to say that statistical decisions on the model specification can drive the estimand, and we don't always know that. And for instance, just to explain why we got these funky results in this little simulation study here on the right-hand side, when we employ the exchangeable GE to estimate the intervention effect in a case where we have no covariates adjusted in the mean model, the coefficient dot over here, that's neither the IATE or CATE. And why is that? And that is because if we derive the limit of this coefficient estimator analytically, that gives us something like this ratio of two expectations that depends on the cluster size, but also depends on rho star, which is the limit of the exchangeable working correlation parameter, the ICC parameter. And we don't know what that value is. And so the target estimate can be really ambiguous if the cluster size is actually informative of the outcome contrast. And so that's not a problem, as we have shown in the other simulations in the first two panels, when either there is no cluster size variation, that's trivial, or the outcome ICC is actually 0, or the cluster size, despite variability, does not inform the within cluster contrast. So it's not informative. And so let's look at GE first, because we have shown in simulations that, we could go wrong if we just specify the model all, by all we want. So we define Lij to be an arbitrary function of the covariates Ci and Xij, and possibly even include the source population size, but that's not needed. It's an arbitrary function of this information. Could also be a null set, so we don't adjust for anything. And the marginal mean model that we investigate comes in this form where we have a treatment indicator with a coefficient, and we have a term that adjusts for additional covariates. And we study the case where we have canonical link functions, so linear regression for a continuous outcome and logistic regression for binary outcome. And the estimation routine is provided in literally every software, and it's based on solving the following estimating equations, where this is commonly known as the generalized estimating equations. And then a common practice is to assume we have a working exchangeable correlation here, because we want to reflect that we have ICC controlled in the estimation routine. And also just to notice that we write YIO and MUIO here to indicate that the GE is fit only on the observed data, that is the subset of MI out of the total source population of size NI. And so that is why the O notation is needed here. And so we know already from the prior discussions that if we fit this model and we derive beta A hat as our target parameter, or interpret that as our treatment effect, the estimand is very unclear. And if we have a lot of covariates, the estimand cannot even be written in a closed form, except that it's the zero solution of this estimating equation. And so to target the estimands that we wanted and we defined early on in a non-parametric way, we propose to use weighted g-computation, where we fit this working model, but then we summarize them in a way and we reweight the predicted outcome in a way so that we could reflect the proper structure of the causal estimand. And so the cluster level estimand, we could summarize the predicted potential outcomes within clusters first, and then we summarize across clusters. And for the individual level estimates, we need to reweight so that we could reflect the target population size in that cluster, and then we summarize across the source population over clusters. And once we have these formulas, we could plug in the mu C hat and mu I hat to create contrast to estimate the cluster average or the individual average causal effects we have defined early on. And we can also develop sandwich variance estimators for these G estimators by using the delta method. So that's operationally quite straightforward. But still, under what condition can we achieve model robustness? Under what condition can we misspecify the model in a way so that we don't compromise the consistency of the target, of the estimator to the target estimates? And so we derived the recipe for model robust inference under the GE paradigm, assuming that we have used the weighted G estimator. And so that boils down to these conditions. Under the assumption we have laid out, if the GE model specification uses any one of the following 4 conditions, we could achieve model robustness in a sense that the other aspects of the model can be arbitrarily wrong in a cluster randomized trials, and we would still get consistent estimator for the IATE and the CAT estimates. And these conditions are A, when the mean model is correctly specified. That's actually very trivial, right? That's something we have studied really well already. And B, when the link function is the linear link function, and we have a Gaussian working variance. That is basically a linear mean model under which we would anticipate the results can be quite special and the results actually hold. Condition C is when we have an independence working correlation. So don't induce undesired weighting by the non-independent working correlation. Use an independence working correlation and you'll be fine, even if we are working with a nonlinear link function. And finally, if we don't stick in individual level covariates in the Lij term, rather we adjust for cluster level covariates or cluster level summaries of the individual level covariates, we'll be fine as well. So as long as our model specification hits one of these 4 conditions, the G model after the G estimator summarization would be consistent to the target estimate we wanted. And so we also create a similar result for targeting the IATE, but under that, we have to weight our GE by the cluster size. And so we don't talk about that in light of time. So this result is quite general because to some extent, it sort of reflects why in the literature, there are quite a few linearly adjusted estimators that are model robust for analyzing cluster level or multi-level data. And so they are actually special cases of the independence GE. And the results also somewhat challenge the conventional wisdom because it does definitely say that if we use an independence working correlation, we are maybe on the better or safer side to get an unbiased estimate, which might be inefficient, but it does remove the bias under incorrect model specification. And so maybe adjusting for cluster within cluster correlation is not that essential. And that reflects a potentially different philosophical path because in the literature of cluster randomized experiments, the arguments for adjusting for correlation and for arguing efficiency is grounded on a correct mean model. Only when the mean model is correct, we can talk about efficiency. But here, if we enlarge the model space where the mean model may even be incorrect, then we actually have to rethink that recommendation, and maybe the working independence correlation is a safer choice. And on the other end, we have derived a similar result for the covariate adjusted linear mix model by viewing that linear mix model could be very similar to the generalized estimating equation under condition B, where we have a linear link function and a Gaussian working variance. And so linear mix model basically just uses a different way to estimate the variance component parameters than GE. And so in that sense, they're quite similar. And so we have result 2, which demystifies the recipe for model robust inference under linear mix models, very similar to GE. However, the results are not available for generalized linear mix model and as expected because these models are complex. And so the likelihood derivations are very untractable. And so we are not able to derive anything similar for generalized linear mix models, even though empirically that's something that's good to study in the future. And so adapting model-based methods are attractive, but there are pieces where we intentionally misspecify the working model to achieve estimand aligned inference, right? And in addition, we have assumed an assumption of within cluster sampling that is completely agnostic of any cluster level features, which could be a little implausible. And furthermore, it does not open the door to a wide class of working models we have access to in the multi-level data context. And we might miss a chance to maximize efficiency and power in this context. And so because of these potential limitations, we want to develop more principled estimators to simultaneously optimize covariate adjustment and address possible observed cluster size arising from post-randomization cluster-dependent sampling schemes. So each cluster feature can dominate or determine how we sample the individuals within clusters. And for that, we are going after the efficient influence function under our framework to shed light on possibly improved or optimal estimators. And just to give a quick overview of this framework, where we leverage the concept of efficient influence functions, or EIF, as an estimand-oriented tool that characterizes the sufficient information from the data that could inform the estimand in an optimal way. And then these efficient influence functions will suggest nuisance functions that are key components of working models we want to fit to the data. And then we could assemble the nuisance functions to derive an EIF-based estimators. And if these nuisance models are correctly specified, say by machine learners, we arrive at the possibly most efficient estimators that achieve the asymptotic variance lower bound that's characterized by the variance of the efficient influence function. So that's going to be just an overarching workflow to say that if we can go after this efficient influence function, we might have improved estimators that could improve the conventional estimators we fit on a daily basis. And so we first relax assumption 3 by allowing the potentially observed cluster size MA to further depend on the source population size and possibly the cluster level covariates. Let's say a rural hospital or an urban hospital, they might have a different sampling scheme implicitly. And this would also accommodate the situation where we have full enrollment, where we basically set MI equal to NI. So we have no second stage within cluster sampling. And just to note that, allow the cluster size to depend on covariates is actually a form of selection bias that we could possibly address under this condition. But we do not we do not cover the more complex cases where enrollment may depend on individual covariates, which might happen, but our approach right now doesn't really accommodate that more complex situation. And so we focus on estimating the cluster level average causal effect, and we derive this efficient influence function for targeting that cluster level average potential outcomes. And it does possess this slightly more complicated form than what we may be used to in the doubly robust causal inference paradigm, where we might only have 2 terms. Here we have 3 terms. The first and third term are relatively familiar because they resemble the context of a doubly robust estimator in observational studies. But the second term arises because we do have these second stage within cluster sampling that might depend on covariates at the cluster level, as well as the source population size of each cluster. And so we need to take that into account in this derivation of the efficient influence function. The efficient influence function suggests 3 working models. The first one is the expectation of the observed cluster level mean as a function of the treatment assignment, the within cluster covariates, and the cluster level characteristics, including the cluster source population. The second model is a little simpler. It's not conditioning on the covariate. It's only conditioning on the treatment and the cluster level information. The third model is the propensity score model at the cluster level, which is the probability of the assignment given the cluster level information, including the observed cluster size, the source population size, and the cluster level covariate. And based on these, we could develop two possible ways to proceed, one of which is to fit parametric models, whatever these models are, for each of these working models, and then assemble them to derive a plug-in parametric estimator. And the second strategy, which is appealing in the modern causal inference literature, is to leverage machine learning algorithms with cross-fitting to flexibly learn each of these working models. And we derive a fully efficient estimator because these models were supposed to be correctly specified. They could remove restrictive conditions or assumptions in the parametric regression concept. And so we show that if we consider the parametric route, when we correctly specify the cluster level propensity score model, or when the mean outcome model are compatible in a sense that they are equivalent when conditioning on the cluster level information, we get a consistent estimator to the target estimand, and we can derive their asymptotic variance and derive a plug-in variance estimator. And in addition, if we are going after the route of machine learning estimators, once we assume that these functions can be learned at a rate that is lower than the parametric rate, but at least an m to the fourth rate in LP in the L2 norm, then we can show that the machine learning based estimator under this efficient influence function construction is also consistent, and furthermore, it achieves the efficiency lower bound asymptotically that's characterized by the variance of the efficient influence function. And despite the complexity of this theorem, of this result, what the overall message is that we could have a doubly robust estimator that opens the door to a wide class of covariate adjusted working models. And once we get one of these two conditions correct, then we get a consistent estimator to the target estimand we wanted. In addition, if we have full enrollment such that the cluster size we observe is equal to the underlying source population size, then in this estimator, only F1 hat remains. And the resulting estimator is robust to arbitrary model misspecification because the underlying construction of the efficient influence function is much easier, and we don't have these additional working models we need, and the estimator becomes actually more robust. We could misspecify F1 however we want, and we get a consistent estimator. And intuitively, that's because F3 is trivial and is always correctly specified. And we also have the parallel results for the target estimand IAT, even though that's not shown here. And so we've done some simulation studies to validate these conjectures on the model robustness and potential improvement of this efficient influence function-based construction over these routinely considered model-based estimators under various scenarios that cover binary and continuous outcomes, small number of clusters and large number of clusters, or different sampling schemes, as well as nonlinear complex data generating mechanisms. And first of all, just to give a snapshot for the results, we're estimating the cluster level average causal effect, where we compare the machine learning based estimator versus the G estimator derived from the GEE fitting with one of these four conditions. And we see that in terms of coverage, when assumption 3 is violated, where we actually have cluster dependent sampling, the machine learning based estimator is actually much more robust, where the G computation estimator from the G estimator can deteriorate and have a lower coverage. And this lower coverage is mainly coming from the fact that the G estimator is actually biased. And in addition, we have shown that both the GE estimator under a G computation construction and the machine learning estimator can improve efficiency over the unadjusted analysis in a cluster randomized experiment. And sometimes there is a much more dramatic improvement under machine learning versus GE, but sometimes otherwise. And so it depends on how the data is actually generated. But overall, it seems that there are more scenarios where the machine learning estimator dominates the efficiency of the GE or model-based estimator. And so we apply these estimators to illustrate their performance under 3 cluster randomized trials. We collect 3 cluster randomized experiments with varying conditions, such as the number of clusters as well as the cluster size distribution. We see a spectrum here from many clusters with small cluster sizes and fewer clusters with relatively large cluster sizes. And we test out the performance of these estimators. And we focus on looking at the GE estimator under g-computation and the efficient influence function-based machine learning estimator. And we see that they both improve over the unadjusted estimator because they could shrink the confidence interval for estimating both the cluster average and the individual average estimand in this context. And so we tabulate the observed relative efficiency, which is based on the variance estimates. This quantifies to what extent we could shrink the length of the confidence interval in a single data realization. And we see that both estimator could improve over the unadjusted estimators without compromising the validity of the inference in terms of the target estimates, but the relative efficiency between these different adjustments could be a case-by-case evaluation or study. And just to summarize, for the sake of time, in this work, we adapted these conventional model-based inference tools to estimate 2 classes of estimands in cluster randomized experiments through g-computation. And we recognize their limitation and further propose new estimators that leverage covariates to maximize efficiency and possibly address cluster-dependent sampling scheme. And as I mentioned, one potential challenge in this framework is that it does require some knowledge of the source population size, and we treat that information as a cluster level attribute. And depending on the application, this might or might not be possible. For instance, if we are randomizing schools or classrooms, we have a relatively well understanding of the source population size. But if we are dealing with hospitals or clinics, it might be a little bit more challenging if we don't have any historical data. However, the fact that the estimands depend on the population size, that's an inherent feature of the estimand. And so maybe it does invite some thinking on better practice when we plan a study. Should we get information? Should we work hard to obtain information on what population are we trying to study? On what population size are we talking about when we evaluate intervention in this real-world context? And finally, there are possibilities where we basically just set our population size to the observed cluster size and assume that we have sampled everybody in the cluster. That would simplify the problem, and the efficient influence function-based estimator should still proceed with very minimum modifications. And just to say that, this work is a thinking process to possibly change or challenge conventional wisdom, where we depend on models to generate causal inference. Here we are talking about what is going to be the framework under which we could generate the same rigor in analyzing cluster randomized experiments compared to what we have already in this world of traditional RCT, where we have individual randomization. And for this, the framework, the estimands are super important, and then estimand aligned model assisted inference that could tolerate model misspecification would be desired. And this work, it reflects this underlying thinking to challenge conventional wisdom that depends on models. And just to say that this talk is based on a manuscript we have archived last year, and this work is led by Bingkai Wen, who is going to be an incoming assistant professor of biostatistics at Michigan, and this work is supported partially by my P4 grant. And so thank you so much for your attention, and I welcome any comments and questions.
Thank you very much for this brilliant lecture. It was very interesting. So If anybody from the audience has questions, please put them in Q&A. I guess I have a small question. If you could tell us a little bit about the examples, so what type of experiments and trials, a little bit more about these trials that were conducted using this paradigm.
Yeah. So I admit that I did gloss over this part because of time, and so I think generally in this work we are focusing on a two-arm cluster randomized trial where we randomize, let's say, hospitals or clinics to receive interventions, and in these studies, oftentimes the cluster size is variable. It's very unlike the world of longitudinal data where we do have like scheduled measurements of each individual, and an individual as their own cluster have, everybody has like 5 measurements or 6 measurements. In this context, it's hard to project how many individuals are going to be in each cluster. That depends on the characteristics of the cluster, the nature of the intervention, the context of the study. And so in all of the 3 trials we have looked into, the cluster sizes are heterogeneous. They range from, let's say, 1 to 10, or range from 3 to 50. So, we are targeting this context where the cluster size is an important feature of the study and actually contributes to the estimands. And so all of the studies we have looked at right now in this slide reflects that thinking as well.
So I also had a question to kind of help, because I'm also new to cluster randomized trials, and so we just got like a collaborator who wants to run one, and so I want to better understand, what do you mean? Can you give me an example of a setting whereby you have this cluster dependent sampling issue? That seems to mean that you definitely should not be using the GE methods in that context.
Right. Yeah, that's a very good question. I think so this actually arises very often. Like, for instance, there are occasions. So first of all, under both assumption 3 and assumption 4, the cluster size can depend on the intervention condition. This, first of all, is pretty common, because if we're not really blinding the study, then patients might want to seek interventions. Like, they know, oh, that hospital implements a novel technique to improve provider-patient communication. I want to be there. So they would self-select into those intervention conditions. And so you might end up seeing more individuals in the intervention arm than the control arm. And it's very, very common, and people would flag that as a potential selection bias. The cluster-dependent sampling says that we could go a little bit further. In addition to the dependence on the intervention condition, we could allow the source population size to play a role. Like, for instance, if we have an urban hospital that already accommodates a larger population who are seeking care, then we could assume that we have access to more individuals for the specific study, and that recruitment could be proportional to the underlying source population, which is larger than those in an urban, like in a rural hospital. So that could be one situation. Or the cluster level covariates could be, let's say, number of providers, number of physicians that are specialized in this intervention. And so they might play a role in getting more patients in those clusters as well. Yeah, but it does not address the fact that, individuals based on their, let's say, very important and prognostic health conditions, they might self-select. So that's a more challenging problem we currently don't address.
We also have a question from the audience. Jerry Chang is asking, does it make a difference for efficiency gain in terms of adjusting cluster level versus individual level covariate in the treatment propensity score model?
Yeah, that's a very good question, and I think is a question that is worth investigating empirically much more. I admit we haven't looked into that. a lot of the simulations were trying to make sure that these approach actually would work and they improve upon either model-based methods or the unadjusted methods, which are still commonly used in the primary report in many published trials. So in this construction, the propensity score model is actually a cluster level propensity score model. It's not an individual level propensity score model. And so even if we want to adjust for individual level covariates, we have to treat them as cluster level summaries. But the question regarding whether there is going to be additional efficiency gain by adjusting for X bar beyond those offered by C, I think is a really good question that is worth studying. And we haven't really looked into that. And the gain might be marginal, given that this estimator is pretty complex and we have these complex outcome model that already adjusts for X's, but it could be, an improvement. So I think that's something we haven't really answered, but worth studying for sure.
I guess we don't have any more open questions from the audience. So, and we're kind of out of time. So thank you so much. It was wonderful to have you. Thank you for sharing all this important knowledge with us. Yeah. Thank you.
Thanks a lot.
Thanks very much.
Thank you.
Thank you.